It's really nice having Dave and Jesse really set the stage for this, so there's really not much need to go into the background on whitebark, into whitebark pine, since we've heard that. But I'd like to start by just acknowledging my co-authors, Jeff Hickey, Hagenius Preisler, and Ken Raffa. So our objectives were to try and understand the climate effects, quantify the climate-beetle relationships, specifically in whitebark pine. A lot of work has been done in lodgepole pine, but comparatively little in whitebark. Then we wanted to understand the causes of the recent outbreak, ultimately to be able to look at what are the historical through the weather suitability for beetle outbreaks in whitebark pine. We did this with statistical modeling. We're modeling the probability of tree mortality, whitebark pine mortality, and there are several things we know we need to include in the models. One is beetle pressure, how many beetles are available out there to kill trees. Another is stand structure, what is the diameter and composition of the stands. And then several of these climate factors. First, beetle adaptive seasonality, their development is temperature driven. So how the adaptive seasonality means that they can develop in 1 year and they all emerge at the same time in late summer to have a mass attack on trees. So we had several different variables, from very specific variables coming from process models developed by Jesse Logan and others to more general monthly temperature variables. Then beetle winter mortality is another important part of the picture, as Jesse mentioned. Cold snaps can be really important, so that before they've developed the antifreeze in their bodies to withstand. So again, we had multiple variables from a cold tolerance model, again, that Jacques Renier and Jesse Logan and Barbara Bentz and others have worked on, to more general monthly variables. And then finally, tree drought stress. And this is the one that for whitebark is really the least well understood. Because of the difference in the chemical composition, can whitebark defend themselves? Are they really being attractants instead of defending? So we wanted to estimate what is drought stress. And this, we used climatic water deficit, monthly precipitation, vapor pressure deficit, a suite of variables. The mortality data comes from the Forest Service Aerial Detection Survey data, and this is gridded to 1 kilometer. So we're looking at the landscape in a 1 kilometer resolution. Then the beetle pressure variable also comes from the number of trees killed last year. Then all of the climate variables, we used primarily 2 sources. One is PRISM, 800-meter PRISM monthly data, and then the second are the several daily process models that are on a daily time step. And this part of the model itself, it's a logistic regression, a generalized additive that allows for nonlinear relationships. So then we wanted to develop this model so that we could estimate weather suitability. So after going through a model selection process, coming up with the best model, which representing all of those different processes, we applied it to historical weather using PRISM data from 1900 through 2009, and then to future climate data. And here we used downscaled to 1 kilometer from the NASA NEXT database, 10 different GCMs under 3 different emission scenarios. RCP 2.6 is the latest definition for the low emission, 4.5 is the middle, and 8.5 is the high. Then to calculate a weather suitability index, we can do this in 2 ways. One is the sum of all of the weather terms in the model, and the second is the individual weather terms in the model. So these are the results. The best model, adaptive stand structure, this is the one we have not a lot of great information for across at this resolution and spatial extent, but we use the percent whitebark pine, how many 30-meter pixels within each 1 kilometer cell were identified as whitebark pine. Adaptive seasonality was best represented by the average fall temperature. Warmer temperatures led to the greater chance of tree mortality. Beetle winter mortality was best represented by winter average temperature. Again, higher temperatures led to more tree mortality. Both of these plateau, so that The curve goes up and then plateaus where increasing the temperature has no more effect. In the winter, that makes sense. The beetles have survived, so anymore, they've all survived. And tree drought stress was best represented by the cumulative 2-year summer precipitation. And we looked at a lot of different variables here. Is it water year? Is it summer? Is it winter? Is it water deficit? And this really simple precipitation, summer precipitation, was the best. And less precipitation, more drought stress led to more tree mortality. But there's a little catch to this one that I'll show you. This is just looking at how well the model fit the data, and the black are the observed area with mortality, red is predicted, and it missed what was happening here, but it did capture some other declines. And so beetle pressure is a variable in this model, and so if it just went increasingly up always, then we wouldn't have a lot of confidence in it. But because it is able to capture some of these declines, even though beetle pressure was much higher the previous year, then we feel like we can use this to make some inferences about what has happened and what may happen. So this graph on the y-axis is the term from the model. It's the log odds of winter mortality is shown here. So as this is very suitable, above 0 it's a suitable winter temperature, below 0 is unsuitable, it's very cold. And it's plotted from 1900 through 2009. And the black line is the recent outbreak, the area with mortality. And so the biggest change, I think, from the whole model that when looking backwards in time is that there were a lot of years in the past that were simply too cold. And we've heard this, that it's the change in temperature that has allowed these outbreaks to happen. And this modeling supports that as well. When just a few years actually prior to the outbreak beginning, temperatures got warm. They got maybe a little too cold, maybe not, and then they remained suitable for the rest of the outbreak. So the beetles were not being limited by winter temperatures any longer. This is the fall temperature. There's not anything like as much variation. There's been a few times in the past where it's been too cold, but mostly fall temperature regulating the adaptive seasonality component and synchrony of the population has not had as much effect as the winter mortality component. And this is summer precipitation. And this one is a lot more variable. At this point in time, when the population, winter temperatures got suitable, there was no drought stress. It was very wet. But then there was a period with some drought, and the beginning of the outbreak, maybe contributing, maybe not. But once the outbreak begins, the patterns of mortality do track the pattern of precipitation really well. So this, I think, is fairly inconclusive, although seeing what Dave just showed us, maybe that it does combine some more support that precipitation and drought stress is an important factor, although the populations were building in the absence of drought stress for the beginning of this outbreak. Now I wanted to try and put it all on one figure to look at where we are, where have we been, and where are we going. So these axes are change in temperature, change in precipitation, and this is the average 1950 through 2005. The contours are the odds ratio. So this is on the 1. You know, it's the odds of beetle mortality or tree mortality from beetles due to weather conditions. So this is the period of no outbreaks, just prior to the recent outbreaks. This is in the late 1980s, early 1990s. It was cooler and wetter. This is the outbreak period relative to the historical conditions. It was warmer and drier. This is the range bounded by those 10 GCMs forced with RCP 2.6. And this scenario, it not only assumes that we get carbon emissions under control, it also assumes that we figure out some sequestration. And so temperature declines into the future with this scenario. This is the area bounded by 4.5, the sort of middle ground. and this is bounded by 8.5. And if you look at the carbon emissions right now, this is the track we're on. We're not on 4.5, we're on 8.5. But there's obviously a lot of variation, particularly here on the precipitation on the y-axis. So this is looking from 1950 through 2099. The black is the model applied to PRISM data here. This dark black line is the average of the 10 GCMs, and the gray is the range bounded by those. This blue is a wet model. The red is a dry model. So you can see that is having, according in this model, the amount of precipitation is having a large effect on what the overall weather suitability would be. But that doesn't, the models all agree much more on temperature. It's getting warmer. It's harder to predict, forecast precipitation. It's easier to forecast temperature, and there's not much difference. Looking at about 2039 or 2035 or 40, on average, if we use those 10 GCMs as to say what might the future look like, they're all saying the winters are warm enough to support a beetle outbreak. This is just looking at that spatially. What's the probability in these time periods? This is 1960 to 1999, then 30 years from 2010 to 2039, 2040 to 2069, 2070 to 2099. What's the probability of there being a winter warm enough to support beetle populations? And there are some places, you know, as Jesse was talking about, in the Wind Rivers, on the Beartooth Plateau, that are cold and that have, where the outbreak has been slower to develop and the mortality has been less severe. But as we get out into the future, those places won't act as, they're not going to be that cold anymore. So echoing what Jesse said, I think management, you know, it is important to think about where we want to go with the species and focusing on those areas that part of the ecosystem that are colder or that have cold air drainage. You know, certainly that is not captured in global climate models. So that's important for us to think about on the ground so that we can provide some refugia. But ultimately, we as a society need to reduce carbon emissions, or these refugia are really just going to be hospices for whitebark pine. I'd like to thank our funders, primarily the Northwest Climate Science Center and our advisory committee, and thank you all for your attention.